the problem. So ABCD is a continuous beam. So in this beam, you're going to see AB is having a UDL of 20 kilonewton per meter. So which is of 6 meter span. And the moment of inertia is twice. Whereas for BC span, it is 80 kilonewton, which is at the center of this beam. And the span here is 4 meters. Moment of inertia is I. And whereas CD is a overhang portion. So for this portion, you're having a distance of 2 meters. So it is carrying a point load of 40 kilonewton. So now in this lecture, you're going to analyze the continuous beam by using a slope deflection method, and you're going to draw the elastic curve, bending moment, and shear force diagram. So coming to the step 1, you're going to determine the degree of freedom. So coming to the degree of freedom, so A support, if you just take, so this is a fixed support. So here you are having rotation as 0, as well as translation is 0. That is theta and delta are 0. Whereas coming to the B support, so here theta is not equal to 0, that is rotation. And delta is equal to 0. So that is your translation. And coming to C also, here the rotation is there. And whereas the translation is not there. So that means here you are having a degree of freedom to be 2. So that is degree of freedom is equal to 2. So here 2 unknowns are there. So that is theta B and theta C. So this is your step 2. Sorry, step 1. Now coming to your step 2. So in step 2, you're going to calculate the fixed end moments. So in the step 2, you're going to write calculation of fixed end moments. So here what we are going to do is, whatever the supports are there, we are going to take all the supports to be a fixed supports. So here I am just drawing in individually beams. So you can just take, this is your AB, and similarly BC, so this is BC, and this is CD. So it is having a UDL of 20 kilonewton per meter. So which is of 6 meter span. And this is also we are having 80 kilonewton. So which is at the center, that is 2 meter, 2 meter. And here you are having a 40 kilonewton, which is of 2 meters. So for this, we are going to write the fixed end moments. So coming to the fixed end moment, so here the fixed end moments that is developed at A will be in this way. Hogging moments are going to develop for AB. Similarly for BC also, and this is for CD. So the moment that is going to develop at A is WL square by 12, and here also it is WL square by 12. Whereas for the point load, it is at the center, it will be WL by 8, and this will be equal to WL by 8. Okay. So this one anyway, we are going to take it in the equilibrium condition. Okay. So this is an end moment that is going to be developed at this portion. So that end moment, I am going to take it as MCD. So that will be equal to, so this is in hogging in nature. So that is minus, which is in anti-clockwise direction. So minus 40 into 2. So that will be equal to minus 80 kilonewton meter. Okay. Now coming over here, I am going to calculate the fixed end moments. So here MFAB will be equal to, so here this way it is in anti-clockwise direction. So as per sign convention, it is minus WL square by 12. So that is minus 20 into 6 square by 12. So what is your MFAB value? So MFAB value will be equal to minus 60 kilonewton meter. Similarly, what is your MFBA? So MFBA will be equal to plus WL squared by 12. So why? Because this is in clockwise direction. So this will be equal to plus 20 into 6 squared by 12. So MFBA will be equal to plus 60 kilonewton meter. Now coming to this BC portion. So here MFBC will be equal to, so which is in anti-clockwise direction. So that is minus WL by 8. So that is minus 80 into 4 by 8. So that will be equal to minus 40 kilonewton meter. Similarly, MFCB will be equal to plus WL by 8. So that is plus 80 into 4 by 8. So that will be equal to plus 40 kilonewton meter. So this is positive. Okay, so here MFCB will be equal to 40 kilonewton meter. So this is a step 2 while calculating the fixed end moments. Now coming to your step 3. So step 3 will be equal to slope deflection equation. So here you are going to consider a slope deflection equations and you are going to substitute here. So since settlement is not there, so delta will be equal to 0. So delta is equal to 0 since settlement is not there. Therefore, our slope deflection equations will become, so these are the standard slope deflection equations. So MEAB will be equal to MFAB plus 2EI by L into 2 theta A plus theta B. Okay. Similar way, MBA also will be equal to MFBA plus 2A by L into 2 theta B plus theta A. So here I am going to substitute the values here. So this will be equal to minus 60 plus 2E into moment of inertia will be equal to 2I. And whereas the span here will be equal to 6 meters and 2 theta A plus theta B. So this is your MAB, momentum. So just I am going to draw the figure. So here we are considering AB, BC, and this is an overhang portion. So this is A, this is B, this is C, and this is D. And it is having a UDL of 20 kilonewton per meter. And this is of 80 kilonewton. And which is of center, that is 2 meter, 2 meter. And this is 6 meters. And this is 4 meters. And moment of inertia is 2I. And here the moment of inertia is I. And this is for 2 meters. So which is of 40 kilonewton. Okay. So here I can write theta A is equal to 0 from this boundary condition. So I'm going to substitute here theta A is equal to 0. So now MAB will be equal to minus 60 plus 2EI into theta B by 3. So this is your equation 1. Now similarly, MBA will be equal to MFBA plus 2EI by L into 2 theta B plus theta A. So here theta A is 0. Now substituting these values, you are going to get MBA will be equal to plus 60 plus 2E into 2i by 6 into 2 theta b. So that will become 60 plus 4 by 3 ei into theta b. So this is a second equation. Now coming to the next one. So that is your MBC. So MBC will be equal to MFBC plus 2EI by L into 2 theta B plus theta C. So here theta B and theta C both are your unknowns. So you can just substitute. So here your MBC value is minus 40. So this is minus 40 and moment of inertia is I only. So it is 2I by, the span here is 4 meters. So 4 into 2 theta B plus theta C. So this is your MBC. So coming to your MBC, your simplified equation will become minus 40 plus EI into theta B plus 0.5 into EI into theta C. So this will be your third equation. Now coming to your another next equation, that is MFCB. So MFCB will be equal to, MCB will be equal to MFCB plus 2EI by L into 2 theta C plus theta B. So here I am going to substitute plus 40 plus 2EI by 4 into 2 theta C plus theta B. So this is your MCB. So now your MCB will be equal to 40 plus 40 plus EI into theta C plus 0.5 into EI into theta B. So this will be your equation 4. Now this is your step 3, that is slope deflection equations. So these are the 4 equations you are going to get here. Now next step is you are going to use the equilibrium conditions. Next step 4. Step 4 will be your equilibrium equations. So coming to your equilibrium equations, we'll just see the figure. So for this figure, you can just see 2 joints are there, that is B joint and C joint. So for this B joint, sigma MB will be equal to 0, and for this C joint, sigma MC will be equal to 0. So I am writing here equilibrium conditions. Sigma MB will be equal to 0. So this implies MBA plus MBC will be equal to 0. So this is first equation. Another equation is sigma MC will be equal to 0. This implies MCB plus MCD will be equal to 0. So this is the, this is fifth equation and this is the sixth equation. So by solving these 2 equations, so unknowns are again theta B and theta C. So you are going to solve the equations, right? So now I am going to consider MBA plus MBC. So first is MBA plus MBC. So what is your MBA equation? So MBA equation will be equal to 60 plus 4 by 3 EI into theta B. Okay. So MBC equation is minus 40 plus EI into theta B plus 0.5 into EI into theta C will be equal to 0. So by simplifying this equation, you are going to have 2.33 EI into theta B plus 0.5 into EI into theta C will be equal to minus 20. So this is the seventh equation. Now coming to next one, MCB plus MCD. So this will be equal to MCB. So MCB will be equal to 40 plus 0.5 EI into theta B plus EI into theta C. Okay, so what about your MCD? So we know that, just we'll go here. So MCD is nothing but, so the moment that is going to be developed at this portion. So what is the moment that is developed at this portion? 40 into 2 kilonewton meter. So that is MCD will be equal to minus 80 kilonewton meter. So here I am going to write MCD will be equal to minus 80 will be equal to 0. So by simplifying this equation, you are going to have 0.5 EI into theta B plus EI into theta C will be equal to 40. So this is the 8th equation. So by solving these two 7 and 8 equations, you are going to get theta B and theta C. So our next thing is, by solving equations 7 and 8, we get theta B will be equal to and theta C will be equal to. So theta B, you are getting it as minus 19.2 by EI, and whereas theta C, you are getting it as 49.62 by EI. So the negative indicates that it is in anti-clockwise rotation, and whereas positive indicates that it is a clockwise rotation. So this one will be equal to clockwise rotation. Okay. So after getting this theta B and theta C, we are going to draw the elastic curve. So just I'll show you how to draw an elastic curve. So this is a beam we are considering, A, B, C, D. Okay. So this is A, B, C and D. So here we are having theta A will be equal to 0. Whereas theta B, theta C we are getting. So theta B here is 19.2 EI. So that is again in negative direction. So just I am going to draw the tangent curve. So here theta A, it is not there. So it is 0 up to some extent. So it is 0 up to some extent. Again, you are drawing downward. Okay. So why we are drawing downward is, so if you draw a tangent to here, and when we make an angle like this, okay, when we take an angle like this, the rotation, so it is getting in anti-clockwise direction. So the curve will be downward. So if you're drawing upward curve, that means the theta B will be in clockwise rotation. So that is positive you are going to get. Okay, so that is the reason we are drawing downward. Again, you are drawing like this. Okay, free and you are going to have some deflection. So when we draw a tangent to here, so here also if you just see, so this is a rotation, and so this is a theta B, so which is of 19.2 by EI, right? So this is in anti-clockwise direction, and now this will be in clockwise direction for this theta C. So that theta C will be equal to 49.62 by EI, which is in clockwise direction. So I'll just write down. So this is anti-clockwise, and here it will be clockwise. So this is how you're going to represent your elastic curve. So this is your elastic curve representation, or you can call it as deflection diagram also. So this is your elastic curve. Now, by getting these theta B and theta C, now you are going to calculate your final end moment. So here we have seen till equilibrium equations. So next step, what we are going to do is step 5. So that will be your final end moment. So step 5 is final end moments. So how you're going to get your final end moments? So we have here MAB, MBA, MBC and MCB. So by using these equations, you are going to calculate your final end moments. Okay. So now our final end moments will be equal to, so MAB will be equal to minus 60 plus 2/3 into minus 19.2. So that is your theta B. So that will be equal to minus 72.8 kilonewton meter. Similarly, MBA will be equal to 60 plus 4/3 into minus 19.2. So that will be equal to 34.4 kilonewton meter. Similarly, MBC will be equal to minus 40 minus 19.2 plus 0.5 into 49.6. So that will be minus 34.4 kilonewton meter. Similarly, MCB will be equal to plus 40, okay, minus 0.5 into 19.2 plus 49.6. So that will be equal to 80 kilonewton meter. So these are your final end moments that we have gotten. So after getting this final end moments, we are going to draw the free body diagram. So what is your free body diagram? So free body diagram will be equal to, so this is AB span, this is BC span, and next will be your CD span. So A, B, C and D. So now you are going to represent your loadings. So the loadings here will be equal to, so this one will be 20 kilonewton per meter and this is 80 kilonewton and this one will be equal to 40 kilonewton. So the span here is 6 meters and here it is 4 meters and this is 2 meters and 2 meters and here the span is 2 meters again. Now, so I'm going to represent the moment. So here MAB you're getting it as negative. So that means anti-clockwise direction of 72.8 kilonewton meter. Again, BA you're having a positive value, so that is clockwise. And BC you're having again negative anti-clockwise, so that is 34.4 kilonewton meter. And CB you're having positive, that is 80. And CD we have already written, that is 14 to 2. Here you're having a hogging moment, so that is 80 kilonewton meter. So this is the representation of your values. I mean moment values. After getting the moment values, we will just write the reactions here. So this is your RA and this one will be your RB1 and similarly this one will be your RB2 and the reaction here will be RC1 and the reaction here will be RC2. Okay. So after making this, so this entire thing we'll call it as a free body diagram. Okay. So for this free body diagram, what we are going to do is we are going to find the reactions first. So what are the reactions here? So for this span, if you just see, so here sigma MB will be equal to, so which is in hogging in nature, so that is minus 34.4 kilonewton meter. So now what is going to happen? Moment about this point you are going to write. So you are going to write moment at this point. 1 second. So moment about this point if you want to write. So that is RA into 6 minus 20 into 6 into 6 by 2. Okay. So minus 72.8 will be equal to minus 34.4. So from this you are getting RA will be equal to 66.4 kilonewton. Whereas RA plus RB1. So that means here it is sigma Fy. Sigma Fy will be equal to. So RA plus RB1 will be equal to 20 into 6. So that is the external load. So from this you are getting RB1 value to be 53.6 kilonewton. So this is RA and this is RB1. So that means it is 66.4 kilonewton and this is 53.6 kilonewton. Okay. So next, for this sigma MB will be equal to, about this point only we are considering. So that one will be equal to again hogging moment. So that is minus 34.4 kilonewton meter. So that means RC1 into 4 minus 80 minus 80 into 2 will be equal to minus 34.4. So now RC1 will be equal to 51.4 kilonewton. Now RB2 plus RC1 will be equal to 80 kilonewton. So from this RB2 will be equal to 28.6 kilonewton. So this is the reaction you are going to get. So this one will be equal to 28.6 kilonewton and RC1 will be equal to 51.4 kilonewton. Whereas coming here, RC2 will be equal to 40 kilonewton. So that is, this one will be equal to 40 kilonewton. So this is how you are going to have your free body diagram. Okay. So after getting this free body diagram, so I'm going to once again, I'll draw the figure now. So by using this figure, we are going to draw the shear force diagram and bending moment diagram. So here, we'll just draw. So for this, you are having 20 kilonewton per meter. So this is A, B, C and D. So this here for CD it is 40 kilonewton and for BC it is 80 kilonewton and this is 2 meters, 2 meters and here also you are having 2 meters and for AB it is 6 meters. So just representation of all the values now. So moments I am going to represent now. So this moment is 72.8 kilonewton and this moments are 34.4 kilonewton and these moments are 80 kilonewton. Next, after this, what are the reactions we are getting? So the reactions here are, so here RA, so this is 66.4 kilonewton and RB1 will be equal to 53.6 kilonewton. RB2 you are having again 28.6 kilonewton. And now coming to your RC1, it is 51.4 kilonewton. And RD again, RC2 you are having again 40 kilonewton. So this is the free body diagram. So for this free body diagram, what we are going to draw is you are going to draw the shear force diagram and bending moment diagram. So the bending moment diagram, first we'll draw the shear force diagram, then we'll draw the bending moment diagram. So the shear force diagram represents here. So just draw a straight line. So which is of A, B, a C and D. So here you can just see it is something like a simply supported beam which is carrying a UDL. So now ours will be equal to, this is 66.4 66.4 kilonewton. So again, I told you here it is in the clockwise direction. So clockwise direction will be a positive shear. Anti-clockwise direction will be a negative shear. So here B pot we are having an anti-clockwise shear. So that is anti-clockwise direction. So it is a negative shear. So which is of 53.6 and it will be linearly varying. So this value will be 53.6 kilonewton. So this is positive and this is negative. Again here RB2 you are having a clockwise direction. So which is of positive shear. And again at C you are having an anti-clockwise direction. So it is a negative shear. So which is of 51.6. And this is of varying like this. Why? Because it is a point load. So this is positive, this is negative. So again here it is 34.4 kilonewton and this is 51.4 kilonewton. And coming over here, it is again a positive shear. That means clockwise direction at C portion. So it is 40. So which is of some high value. So here at this portion you are having nothing. So it will be 0. Sorry. So here also you are having a 40. 1 second. So it is having a clockwise shear. So it is a clockwise shear. So clockwise direction. So both will be equal to 40 only. So this is a positive value of 40 kilonewton and 40 kilonewton. So this is your entire shear force diagram. So you can just shade this shear force diagram like this. This is how you are going to represent. So where the moments are not getting influenced for a calculating of a shear force. So here only the reaction part and the external forces, external loads that are acting will come into the picture. So this is the entire shear force diagram. So we can directly follow the sign convention like I'll just show you. So clockwise moment you are getting means it will be a positive shear. Anti-clockwise moment means you are getting a negative shear. Just I'll show you. So here you can just see if you just take a segment. So when your arrow is heading upward and downward. So when you take a section here, so this is left hand side and this is right hand side. Towards your section, if it is making like a clockwise direction, so then it will be positive. Similar way, when it is making a negative direction for your section, that means anti-clockwise. So this is in anti-clockwise direction. So this is left and this is right. So then this is a negative shear you are going to get. So this will be your free body diagram, up one, and this one will be your shear force diagram, downward. Okay, then after drawing your shear force diagram, then we are going to make a bending moment diagram. So to draw the bending moment diagram, so we'll just see. So due to this external load acting, so that bending moment diagram acts like a simply supported one. So for this reactions, you're going to have the bending moment diagram to be a parabola. Then afterwards, the intersection portion will be your final end moments. So we'll see that. So coming to this again, we will draw. Okay, so this is A, this is B, this is C, and this is D. So for this, simply supported beam, you are having AB span is a UDL of 20 kilonewton meter. So that will be a UDL of WL square by 8. So WL square by 8 is 20 into span is 6 square by 8. So that will be equal to 90 kilonewton meter. And again here you are having a point load of center. So that will be double L by 4. So that is load here is 80 into 4 by 4. So that will be equal to 80 kilonewton meter. So these two are in the positive direction. Okay. So now coming to the fixed end moments. So now coming to your fixed end moments. So here at A, you are having 72.8 kilonewton meter. So this one is 72.8. This is the fixed end, final end moments. And here you are having a 34.4. So this is 34.4 kilonewton meter. Again, at this CD portion, you are having 80 kilonewton meter. So that is same thing, 80 kilonewton meter. At free support, you are having a 0. So we'll join all these lines. So this is negative and this is negative. So this is your bending moment diagram. So now you are going to shade the portion. So the shaded portion will be equal to, so this entire thing will be your, this shade portion will be equal to your resultant bending moment diagram. So this entire shaded portion will become your bending moment diagram for the resultant figure. So thank you.